Hey there, science enthusiasts! Welcome to For Science Salah Lotfy channel. Today, I'm super excited to kick off our brand new series on nuclear physics. This course will take us on an incredible journey deep into the core of matter, exploring the fascinating properties of the nucleus and the powerful forces that govern its behavior. Before we dive in, I want to give a huge shout out to Professor Dr. Tarek Farouk Nagla from the Nuclear Power Plants Authority in Cairo, Egypt. His invaluable scientific support has been instrumental in making this series possible. Alright, so why should we study nuclear physics? Well, it's not just about understanding the tiniest building blocks of matter, it's about unlocking the secrets of the universe and harnessing nuclear energy for practical applications. Think about it, from generating nuclear power to advancing medical imaging and cancer treatment, nuclear physics plays a crucial role in our technology and improving human life. Let's dive into some key properties of the nucleus. In this course, we'll be exploring, first, nuclear radius and density. How do scientists measure the size of the nucleus using high-energy scattering experiments? Next, nuclear spin and magnetic moment. We'll look into the quantum mechanical behavior of protons and neutrons inside the nucleus. Finally, binding energy and stability. Why are some nuclei stable while others undergo radioactive decay? Now, what keeps the nucleus together despite the repulsion between positively charged protons? The answer lies in the nuclear force, a powerful yet short-range force that binds nucleons together. We'll discuss its unique properties, like charge independence, spin dependence, and the saturation property, meaning each nucleon interacts mainly with its closest neighbors. This introductory video is just the beginning. In the upcoming lessons, we'll cover the liquid drop model and semi-empirical mass formula to understand nuclear binding energy, nuclear models and quantum mechanics explaining how nucleons arrange themselves, applications of nuclear physics in energy production, medicine, and space exploration. So if you're passionate about understanding the fundamental forces shaping our world, make sure to subscribe and turn on notifications to follow this series. Once again, a big thank you to Professor Dr. Tarek Farouk Nagla for his scientific contributions to this course. Stay tuned for the next episode where we delve into the fascinating world of nuclear structure. In the vastness of the cosmos, everything we see, from distant stars to the very ground we walk on, is made up of atoms. These tiny building blocks of matter are fascinating in their own right, but at the heart of every atom lies a mystery, a tiny realm that holds the key to understanding the universe's most powerful forces, the atomic nucleus. Nuclear physics is the study of this enigmatic realm. It's a journey into the heart of matter, a quest to understand the forces that bind protons and neutrons together in the incredibly dense environment of the atomic nucleus. The importance of studying the atomic nucleus cannot be overstated. It governs the stability of atoms, the energy of stars, and the very existence of elements themselves. By unlocking the secrets of the nucleus, we gain insights into the fundamental workings of the universe and open doors to groundbreaking technologies. In the early 20th century, Ernest Rutherford's gold foil experiment revolutionized our understanding of the atom. By firing alpha particles at a thin gold foil, he discovered that most of the alpha particles passed straight through, while a few were deflected at large angles. This unexpected result led to the Rutherford model of the atom, which proposed that most of an atom's mass is concentrated in a tiny positively charged nucleus at its center, surrounded by orbiting electrons. Rutherford's experiment laid the foundation for nuclear physics. It provided the first glimpse into the structure of the nucleus and opened up new avenues of research to determine its size and properties. The nucleus is incredibly small compared to the size of the atom itself. If an atom were the size of a football stadium, the nucleus would be like a tiny marble placed at the center of the field. Despite its minuscule size, the nucleus contains almost all of the atom's mass. This means that the nucleus has an astonishingly high density, packed with protons and neutrons bound together by the strong nuclear force. To measure the size of the nucleus, physicists use techniques like electron scattering, where high-energy electrons are fired at atoms. The way these electrons are scattered reveals the distribution of charge within the atom, providing information about the size and shape of the nucleus. Just like planets orbiting a star, protons and neutrons within the nucleus possess angular momentum. This intrinsic angular momentum is known as nuclear spin. Nuclear spin is a quantum mechanical property, meaning it is quantized or restricted to specific discrete values. Protons and neutrons are fermions, a type of particle with a half-integer spin. The total angular momentum of a nucleus is the sum of the individual angular momenta of its protons and neutrons. This total angular momentum plays a crucial role in determining the nucleus's magnetic properties and its stability. Section 5. The shell model, organizing the nucleus. To understand the complex behavior of protons and neutrons within the nucleus, physicists developed the nuclear shell model. This model proposes that protons and neutrons occupy discrete energy levels, or shells, within the nucleus, similar to the arrangement of electrons in an atom. The shell model helps explain many observed properties of nuclei, such as their spin, magnetic moments, and stability. Nuclei with completely filled shells of protons and neutrons are particularly stable. The shell model is a powerful tool for predicting the properties of unknown nuclei and understanding the behavior of nuclear matter under extreme conditions. Section 6. Magnetic moments. Tiny magnets in the atomic core. Because protons and neutrons have intrinsic spin and electric charge, they also possess magnetic moments, behaving like tiny magnets. The magnetic moment of a nucleus is the sum of the magnetic moments of its constituent protons and neutrons. Nuclear magnetic moments are influenced by the arrangement and interactions of protons and neutrons within the nucleus. They can be measured using techniques like nuclear magnetic resonance, or NMR, which exploits the interaction of nuclear magnetic moments with external magnetic fields. NMR is a powerful tool used in various fields, including chemistry, medicine, and materials science. Section 7. Nuclear stability. The balance of forces. The stability of an atomic nucleus depends on a delicate balance between two fundamental forces, the strong nuclear force and the electromagnetic force. The strong nuclear force is a short-range force that acts between protons and neutrons, holding them together in the nucleus. It's the strongest force in the universe, but it only operates over extremely short distances. The electromagnetic force, on the other hand, is a long-range force that acts between charged particles. Protons, being positively charged, repel each other through the electromagnetic force. For a nucleus to be stable, the strong nuclear force must overcome the electrostatic repulsion between protons. This balance of forces determines which combinations of protons and neutrons can form stable nuclei and which will undergo radioactive decay. Section 8. Practical applications, nuclear physics shaping our world. Nuclear physics has led to profound technological advancements with far-reaching applications in various fields. In medicine, nuclear physics plays a crucial role in diagnostic imaging techniques like positron emission tomography or PET scans, allowing doctors to visualize and diagnose diseases. Radioactive isotopes are also used in radiation therapy to treat cancer. Nuclear power plants harness the energy released from nuclear fission to generate electricity, providing a significant portion of the world's energy needs. In space exploration, radioisotope thermoelectric generators, or RTGs, utilize the heat generated from radioactive decay to power spacecraft on long-duration missions to the outer solar system. These are just a few examples of how nuclear physics is shaping our world, with ongoing research and development promising even more groundbreaking applications in the future. Atoms are the building blocks of our universe. They make up everything we see, touch, and feel. But what are atoms made of? At the heart of every atom lies a tiny, dense nucleus. This nucleus is incredibly small, yet it holds almost all of an atom's mass. The nucleus is a bustling hub of particles called protons and neutrons, collectively known as nucleons. These particles are bound together by an incredibly powerful force, the nuclear force. The nuclear force is one of the fundamental forces in the universe, alongside gravity, electromagnetism, and the weak force. Understanding this force is key to unraveling the mysteries of the atom and the cosmos itself. Without the nuclear force, atoms as we know them would cease to exist, and the universe would be a vastly different place. The story of the nuclear force is a journey into the heart of matter, a quest to understand the glue that holds the universe together at its most fundamental level. The early 20th century was a time of great upheaval in the world of physics. Scientists were beginning to probe the atom, the smallest unit of matter, and what they found challenged the very foundations of classical physics. The discovery of the nucleus, a tiny, positively charged core at the heart of the atom, posed a profound mystery. How could this positively charged nucleus hold together? After all, like charges repel each other with incredible force. The electromagnetic force responsible for everything from lightning bolts to the bond between atoms should have ripped the nucleus apart. Clearly there was another force at play, a force stronger than the electromagnetic force holding the nucleus together. Enter the nuclear force. In 1935, Japanese physicist Hideki Yukawa proposed the existence of this new force, a force that acted only over incredibly short distances within the confines of the nucleus. Yukawa's theory was a breakthrough explaining how the nucleus could remain stable despite the immense repulsive forces between the protons. The nuclear force is unlike any other force we experience in our everyday lives. It is incredibly strong, the strongest force in the universe over short distances. It's what allows the sun and other stars to burn brightly, fusing hydrogen into helium and releasing immense amounts of energy. This force acts like a powerful glue, binding protons and neutrons together within the nucleus. However, this force is also incredibly short-ranged. It acts only over distances on the order of a femtometer, or 10 to the power of -15 meters. Beyond this distance, it rapidly falls to zero. Imagine trying to stick two magnets together with your hands covered in glue. If the magnets are too far apart, the glue won't stick. Similarly, the nuclear force only comes into play when protons and neutrons are extremely close together. This combination of extreme strength and short range gives the nuclear force its unique character. It is a force of incredible power, yet it is confined to the tiniest realm, the heart of the atom. One of the most intriguing aspects of nuclear forces is their symmetry. Unlike the electromagnetic force, which acts differently between charged and uncharged particles, the nuclear force is indifferent to the charge of the nucleons. This property is known as charge independence. Whether it's a proton interacting with another proton, a neutron interacting with another neutron, or a proton interacting with a neutron, the nuclear force acts with the same strength. This symmetry is a fundamental principle in nuclear physics and has profound implications for our understanding of the universe. It suggests that at the most basic level, protons and neutrons are two sides of the same coin interacting with each other through the same fundamental force. This symmetry is not just a theoretical curiosity. It has practical implications for understanding nuclear reactions, the processes that power stars and drive the creation of elements in the universe. Section 5. The Quantum Dance of Spin. The story of the nuclear force doesn't end with charge independence. It takes an even more intriguing turn when we consider the concept of spin. In the quantum world, particles like protons and neutrons possess an intrinsic angular momentum called spin. Think of it like a tiny spinning top, constantly rotating. This spin isn't just a curious property, it has a profound impact on how nucleons interact with each other. The nuclear force is sensitive to the relative spin orientations of the nucleons. When the spins of two nucleons are aligned, the force is stronger. When they are anti-aligned, the force is weaker. This phenomenon, known as spin dependence, adds another layer of complexity to the nuclear force. It's like two dancers moving in sync. When their movements are aligned, they flow together effortlessly. When their movements are out of sync, it creates a sense of dissonance. Similarly, the alignment of spins in the nucleus influences the strength of the nuclear force, affecting the stability of the nucleus itself. Section 6. Forces in the nuclear playground. So far we've seen that the nuclear force is a complex beast, with its short range, charge independence, and spin dependence. To truly understand this force, physicists have developed sophisticated models. One common approach is to picture the interaction between nucleons as a kind of intricate dance, governed by a set of forces. The central force acts like a spring between the nucleons, pulling them together when they're far apart and pushing them apart when they get too close. The spin-spin interaction, as we've seen, depends on the relative orientation of the spins, either strengthening or weakening the bond between the nucleons. The tensor force acts like a tiny magnet, trying to align the spins of the nucleons. And finally, The spin-orbit coupling links the spin of a nucleon to its orbital motion around the nucleus, adding yet another layer of complexity to the dance. Section 7. Unlocking nature's secrets. Understanding the nuclear force is not just about satisfying our curiosity about the universe. It has profound practical applications, driving innovation in various fields. One of the most well-known applications is in nuclear energy. Nuclear fission, the process of splitting atoms, releases tremendous amounts of energy which can be harnessed to generate electricity. This process is used in nuclear power plants around the world, providing a significant portion of global electricity. Nuclear fusion, the process that powers the sun, holds even greater promise for clean, sustainable energy. By understanding the nuclear force, we can unlock the secrets of fusion and potentially create a future powered by the same energy source that drives the stars. Section 8. Nuclear forces in our world. Beyond energy, the applications of nuclear physics extend to medicine, where techniques like positron emission tomography or PET scans rely on radioactive isotopes to diagnose and monitor diseases. These isotopes, produced in nuclear reactors or cyclotrons, emit positrons, antimatter particles that annihilate with electrons in the body, releasing gamma rays that can be detected and used to create images of organs and tissues. In materials science, understanding the interactions between atoms at the nuclear level enables the development of new materials with enhanced properties. From stronger and lighter alloys for aerospace applications to more efficient solar cells, the applications are vast and constantly expanding. Furthermore, nuclear physics plays a crucial role in astrophysics, helping us understand the life cycle of stars, the formation of elements in supernova explosions, and the evolution of the universe itself. Section 9. A frontier of knowledge. The nuclear force, once a profound mystery, is now a subject of intense study and a cornerstone of our understanding of the universe. Yet, despite decades of research, many questions remain unanswered. What is the precise nature of the force that binds quarks, the fundamental particles that make up protons and neutrons? How does the nuclear force behave under extreme conditions, such as those found in neutron stars? These questions drive ongoing research at the forefront of nuclear and particle physics, pushing the boundaries of our knowledge and challenging us to develop new theories and experimental techniques. The quest to understand the nuclear force is a journey into the heart of matter, a journey that has already yielded incredible insights into the workings of the universe. And as we continue to explore this fundamental force, we can expect even more groundbreaking discoveries that will shape our understanding of the cosmos and our place within it. Deep within the heart of matter lies a realm governed by forces unimaginable in our everyday experiences. This is the world of the atomic nucleus, a realm of incredible density and energy. Here, protons and neutrons, collectively known as nucleons, engage in a delicate dance dictated by the strong nuclear force. To unlock the secrets of this subatomic world, scientists have focused their attention on one of its simplest inhabitants, the deuteron. The deuteron, also known as heavy hydrogen, is a stable isotope of hydrogen. Its nucleus, unlike ordinary hydrogen, contains not one but two particles, a proton and a neutron locked in a tight embrace. These two particles are bound together by the strong nuclear force, the most powerful force in the universe. Understanding the deuteron provides a fundamental stepping stone to comprehending the complexities of the nuclear landscape. The study of the deuteron is not merely an academic exercise, it has profound implications for our understanding of the universe, from the processes that power stars to the development of novel medical imaging techniques. By delving into the heart of the deuteron, we embark on a journey to unravel the mysteries of matter itself. To unlock the secrets held within the deuteron, we begin by examining its fundamental properties. Like a detective meticulously collecting clues, physicists measure and analyze these characteristics to piece together a comprehensive picture of this nuclear duo. One key property is the deuteron's binding energy, the amount of energy required to pry the proton and neutron apart. This energy is a testament to the strength of the strong nuclear force, the glue that holds the nucleus together. Another crucial clue lies in the deuteron's angular momentum, a measure of its rotation. Interestingly, the deuteron's angular momentum reveals that the proton and neutron are not locked in a static embrace but rather engage in a dynamic dance, constantly orbiting and spinning. Further insights emerge from the deuteron's magnetic moment and electric quadrupole moment. These properties provide information about the distribution of electric charge and magnetism within the deuteron. They reveal that the deuteron's charge and magnetism are not uniformly distributed, hinting at the complex interplay of forces at play within this tiny nucleus. By meticulously measuring and analyzing these properties, physicists gain valuable insights into the nature of the strong nuclear force and the structure of the deuteron. To truly grasp the intricacies of the deuteron, we must turn to the enigmatic world of quantum mechanics. In this realm, particles behave like waves, and their behavior is governed by probabilities rather than certainties. Two prominent models, the Yukawa potential and the Wood-Saxon potential, have emerged as key tools for understanding the deuteron's quantum dance. Hideki Yukawa, a pioneering Japanese physicist, proposed that the strong nuclear force is mediated by a particle called the pion. His model, represented by the Yukawa potential, envisions the proton and neutron in the deuteron constantly exchanging pions, much like basketball players passing a ball back and forth. This exchange generates the strong force that binds them together. While the Yukawa potential provides a valuable framework, the Wood-Saxon potential offers a more refined picture. This model incorporates the fact that nucleons have a finite size and are not point particles. It depicts the strong nuclear force as a well, with the proton and neutron residing at its bottom. The shape of this well reflects the complex distribution of nuclear matter within the deuteron. Section 4. Smashing nucleons. A look at nuclear forces. While the deuteron offers a valuable window into the nuclear world, physicists employ a more forceful approach to unraveling the mysteries of nuclear forces' nucleon-nucleon scattering experiments. In these experiments, beams of protons or neutrons are accelerated to high speeds and smashed into stationary targets, mimicking cosmic collisions on a miniature scale. By carefully analyzing the debris from these subatomic crashes, physicists glean crucial information about the nature of the strong nuclear force. These experiments have revealed that the strong force behaves very differently from the familiar forces of gravity and electromagnetism. Unlike these long-range forces, the strong force operates only at extremely short distances, effectively confining nucleons within the minuscule confines of the nucleus. Moreover, these experiments have uncovered the spin dependence of the strong force. Just like tiny spinning tops, nucleons possess an intrinsic angular momentum called spin. Surprisingly, the strength of the strong force depends on the relative spin orientation of the interacting nucleons. This peculiar behavior highlights the intricate and often counterintuitive nature of the subatomic realm. Section 5. The mysterious tensor force. As physicists delved deeper into the complexities of nucleon-nucleon scattering, they uncovered a particularly perplexing feature of the nuclear force: the tensor force. This enigmatic force, unlike more familiar forces, depends not only on the distance between nucleons, but also on their relative spin orientations. Imagine two magnets, their attraction or repulsion dictated not only by their proximity, but also by how they are flipped and rotated. This is the essence of the tensor force. The tensor force plays a crucial role in shaping the deuteron's structure, influencing its binding energy and angular momentum. It also contributes to the deuteron's non-spherical shape, distorting it like a deflated football. Understanding the tensor force remains one of the most challenging aspects of nuclear physics, and its origins are still not fully understood. Despite its complexity, the tensor force holds the key to unlocking a deeper understanding of the nuclear landscape. Its presence has profound implications for the stability of nuclei, the processes that power stars, and even the properties of neutron stars, the densest objects in the universe. Section 6. The deuteron's impact from fusion to medical marvels. The deuteron, while a seemingly esoteric object of study, has surprisingly far-reaching implications for our understanding of the universe and our technological advancements. Its study has led to breakthroughs in diverse fields, from harnessing the power of nuclear fusion to revolutionizing medical imaging. Nuclear fusion, the process that powers stars, relies on the fusion of lighter nuclei, such as deuterons, into heavier ones. Understanding the deuteron's properties is crucial for developing controlled fusion reactions here on Earth, potentially providing a clean and nearly limitless source of energy. In the medical field, deuterium plays a vital role in magnetic resonance imaging, or MRI. Deuterium oxide, also known as heavy water, is used as a contrast agent in MRI scans, allowing doctors to visualize tissues and organs with remarkable clarity. This technology has revolutionized medical diagnostics, enabling the early detection and treatment of a wide range of diseases. The study of the deuteron, a seemingly simple nucleus, has opened a window into the complex world of nuclear physics. Its story highlights the interconnectedness of scientific disciplines and the profound impact that fundamental research can have on our lives. As we continue to probe the secrets of the deuteron, we can expect even more exciting discoveries and technological innovations in the years to come. We begin our journey into the heart of matter, a realm far smaller than the eye can see, the atomic nucleus. Atoms, the building blocks of our universe, consist of a dense nucleus orbited by electrons. The nucleus itself is a hive of activity composed of protons and neutrons, collectively called nucleons. Understanding the nucleus is no easy feat. The forces at play are immense and the particles involved are tiny. Scientists have developed models to represent and predict the behavior of these subatomic particles. These nuclear models are like maps that guide us through the complex terrain of the atomic nucleus. Just like maps, different models highlight different aspects of the nucleus. Some models explain why certain nuclei are stable, while others predict how nuclei decay or interact with each other. Each model offers a unique perspective, contributing to our overall understanding of this fundamental building block of nature. Imagine the nucleus as a tiny drop of liquid held together by powerful forces. This is the essence of the liquid drop model, one of the earliest and simplest depictions of the atomic nucleus. This model draws parallels between the behavior of a liquid drop and the nucleus. Just as the surface tension of a water droplet tries to minimize its surface area, the nucleus experiences a similar force that binds its nucleons together. This binding force arises from the strong nuclear force, one of the four fundamental forces in the universe. The liquid drop model explains several nuclear properties, including the energy required to break apart a nucleus, known as its binding energy. This model considers several factors contributing to the nucleus's overall energy: volume energy, surface energy, Coulomb energy, asymmetry energy, and pairing energy. By considering these factors, the liquid drop model successfully explains the general trend of nuclear binding energies. Moving beyond the simplicity of the liquid drop model, we encounter the shell model. This model draws inspiration from the organization of electrons in an atom, arranged in energy levels or shells. The shell model proposes that protons and neutrons within the nucleus also occupy specific energy levels. These levels, however, are not spatially distinct like electron shells. Instead, they represent different energy states that nucleons can occupy. This model helps explain the existence of magic numbers in nuclear physics. Nuclei with specific numbers of protons or neutrons exhibit exceptional stability. These magic numbers correspond to filled energy levels within the nucleus, analogous to the stability of noble gases with their filled electron shells. Section 4. Collective behavior when the nucleus dances together. While the liquid drop and shell models offer valuable insights, they don't capture the full complexity of nuclear behavior. Enter the collective model, a more nuanced approach that accounts for the collective motion of nucleons within the nucleus. This model recognizes that nucleons don't just exist independently within their energy levels, they can also vibrate and rotate collectively like dancers moving in sync. These collective motions influence the shape and properties of the nucleus. The collective model successfully explains phenomena like nuclear deformation, where the nucleus can deviate from a spherical shape. It also helps us understand the energy levels associated with these collective vibrations and rotations, providing a more complete picture of the nucleus's dynamic nature. Section 5. Complementary perspectives. Comparing nuclear models. Each nuclear model has its strengths and limitations. The liquid drop model provides a good overall picture of nuclear binding energies, but fails to explain the magic numbers. The shell model excels at explaining these magic numbers and nuclear stability, but struggles with deformed nuclei. The collective model handles nuclear deformation and collective motion, but is more complex. It's important to remember that these models are not mutually exclusive. They are complementary tools that provide different perspectives on the same complex system. Like different lenses on a camera, each model helps us focus on specific aspects of the nucleus. By combining insights from these models, we gain a richer understanding of nuclear structure and behavior. This deeper knowledge has profound implications for various fields, from energy production to medical treatments to our understanding of the universe's evolution. Section 6. Unlocking the power of the atom. Applications of nuclear physics. The study of nuclear physics and the models we've explored have led to groundbreaking applications that shape our world. Nuclear power, for instance, harnesses the energy released from nuclear reactions, providing a significant portion of the world's electricity. In medicine, radioactive isotopes, whose behavior is governed by nuclear forces, are vital for diagnostic imaging and cancer treatments. These isotopes help us peer inside the human body and target cancerous cells with precision. Astrophysics also benefits immensely from our understanding of nuclear reactions. The processes that power stars, the explosions of supernovae, and the creation of elements in the universe are all governed by the interactions within atomic nuclei. Section 7. Unveiling the mysteries of the universe, the future of nuclear physics. Our exploration of the atomic nucleus is far from over. Many mysteries remain, driving ongoing research and pushing the boundaries of our understanding. Scientists are constantly refining existing models and developing new ones to explain phenomena like exotic nuclei, which exist far from stability. The quest to understand the fundamental building blocks of matter is a journey into the heart of the cosmos. Each new discovery in nuclear physics not only deepens our understanding of the universe, but also paves the way for future technologies and applications that will shape the future. As we continue to explore the atomic nucleus, we delve deeper into the fundamental forces that govern our universe, unraveling the secrets of matter and energy that bind us all together. We often take the world around us for granted, solid ground beneath our feet, the warmth of the sun. At the heart of it all lies the atom, a universe in miniature. Within the atom's core, the nucleus, a cosmic dance plays out. This dance, a ballet of protons and neutrons, is what we call nuclear reactions. Nuclear reactions are the very essence of the universe. They are the engine of stars and the source of life's building blocks. Unlike chemical reactions, which involve the shuffling of electrons, nuclear reactions delve into the atom's core. Understanding them is about grasping the fundamental forces that shape our existence. Nuclear reactions are a diverse array of subatomic events. Each type of reaction tells a different story about the forces at play within the nucleus. Elastic scattering is like a gentle nudge between two subatomic particles. They bounce off each other without any loss of energy. Think of it as two billiard balls colliding and going their separate ways. Inelastic scattering, however, is a more energetic encounter. In this dance, some energy is transferred, leaving one or both particles in an excited state. Absorption reactions are where things get really interesting. Here, a particle, like a neutron, gets absorbed by a nucleus, forming a heavier, potentially unstable nucleus. Nuclear fission, the process powering nuclear power plants, is a dramatic splitting of a heavy nucleus into lighter ones, releasing tremendous energy. Nuclear fusion, the engine of stars, involves fusing light nuclei into heavier ones, also releasing incredible amounts of energy. Nucleon transfer reactions involve the exchange of protons or neutrons between colliding nuclei. Exchange reactions are a curious swap, where a particle is exchanged between the projectile and target nucleus, leading to the creation of new particles. Each of these nuclear reactions provides a unique window into the subatomic world. By studying these dances, we unlock the secrets of matter's behavior and the forces that govern the universe. Even in the chaotic world of the nucleus, there are rules. These laws, rooted in the fundamental principles of physics, govern every nuclear reaction. One fundamental law is the conservation of mass number. In every nuclear reaction, the total number of protons and neutrons remains constant. Another crucial law is the conservation of charge. The total electric charge before and after a nuclear reaction must always be balanced. Then comes Einstein's famous equation, E equals mc squared. This revolutionary concept tells us that mass and energy are two sides of the same coin. These laws ensure that every reaction adheres to the fundamental principles that govern our universe. Understanding these laws is key to unlocking the secrets of nuclear energy and the very fabric of the cosmos. Section 4. Energy Scorecard, the Q value. In every nuclear reaction, energy plays a starring role. It determines whether a reaction will occur spontaneously or require an energy input. The Q value represents the net energy released or absorbed during a nuclear reaction. A positive Q value indicates an exothermic reaction where energy is released. A negative Q value signifies an endothermic reaction, requiring an energy input to occur. Think of it like a financial transaction. A positive Q value is like a profit, energy is gained. A negative Q value is like a loss, energy is spent. This energy balance is crucial for understanding the feasibility and efficiency of various nuclear reactions. The Q value helps us understand the energy dynamics of nuclear reactions and harness their power for various applications. Section 5, Quantum Weirdness, a peek into the subatomic world. Nuclear reactions are not just governed by classical physics, they also dance to the tune of quantum mechanics. In this strange world, particles behave like waves, and probabilities reign supreme. One key concept is the nuclear cross-section, a measure of the probability that a particular nuclear reaction will occur. Imagine throwing darts at a dartboard. The larger the target area, the higher the chance of hitting it. Another intriguing phenomenon is quantum tunneling, where particles can pass through energy barriers that classical physics deems insurmountable. This bizarre behavior is essential for nuclear fusion in stars, allowing protons to overcome their electrostatic repulsion and fuse together. Quantum mechanics adds an element of unpredictability to the nuclear realm. This interplay of classical and quantum physics makes nuclear reactions a captivating area of study. Section 6. Nuclear reactions in action, from stars to power plants. Nuclear reactions are not just theoretical concepts confined to laboratories. They are happening all around us. Look up at the night sky. The twinkling stars are giant nuclear reactors fusing hydrogen into helium and releasing the energy that illuminates the cosmos. Here on Earth, nuclear fission, the splitting of atoms, has been harnessed to generate electricity in nuclear power plants. While nuclear power comes with its own set of challenges, it remains a significant source of carbon-free energy. In the medical field, nuclear reactions are used in diagnostic imaging techniques like PET scans. Radioactive isotopes are also used in radiation therapy, targeting and destroying cancerous cells with remarkable precision. Even in archaeology and geology, nuclear reactions play a vital role. Nuclear reactions in their many forms have shaped our world and continue to hold immense potential for the future. Section 7, Our Nuclear Future Promise and Responsibility. As we delve deeper into the realm of nuclear reactions, we unlock a future brimming with both promise and responsibility. The development of fusion power holds the potential for a clean and virtually limitless energy source. Imagine a future where energy scarcity is a distant memory. Nuclear medicine continues to advance, offering new treatments for cancer and other debilitating conditions. However, the immense power of nuclear reactions also comes with inherent risks. The specter of nuclear weapons proliferation and the threat of nuclear terrorism serve as stark reminders of the destructive potential of these forces. Ensuring the safe and ethical use of nuclear technology remains one of humanity's greatest challenges. We must harness their power for the betterment of humanity while acknowledging and mitigating the risks they pose. It is through responsible stewardship and a commitment to international cooperation that we can navigate the nuclear future and unlock its full potential for the benefit of all humankind. Section 9. Acknowledgements. I would like to express my sincere gratitude to Professor Dr. Tarek Farouk Nagla for his invaluable contributions to the field of nuclear physics. His groundbreaking research and dedication to teaching have inspired generations of scientists and continue to advance our understanding of the universe's most fundamental forces.